delayed today. We can start, right? Only 10 minutes past. So we can start right away.
So it's live now, I hope. Yeah, it's live now.
Okay. Good afternoon, everyone. Today we have 17th lecture of weekly online lecture series on radar meteorology. It is jointly organized by South Asian Meteorological Association and ACARR CUSAT. So today we have Dr. Ashish Routray. He is scientist F from NCMRWF. He'll be discussing about data assimilation in NWP models. In NCUM models. Before starting the lecture, first I invite Professor Someshwar Das sir for welcome address.
Okay, thank you, Dr. Srikala. Good afternoon, everybody. ABM Professor Ajit Tyagi sir, President of SAMA. Today's distinguished speaker, Dr. Ashish Routray. Our organizing committee members, Dr. Avilas, Dr. Swagata, Dr. Mohan Kumar, Dr. Anikender also I see for the first time today. So Rakesh and all the members of the organizing committee. Very good afternoon. Welcome to the 17th lecture of the lecture series on radar meteorology, being organized jointly by SAMA and ACARR at CUSAT. This is in continuation of our efforts on capacity building of the people of South Asia and member countries and non-aligned movement countries. Today, in fact, since Dr. Ashish is speaking for the first time, so I'd like to say a little bit brief about the lecture series. Most of you know that we have conducted 3 online lecture series till now. This is the 4th one. The first one was on atmospheric physics, which was jointly conducted by SAMA and SRM Institute of Science and Technology. On atmospheric physics, it was conducted for about 4 months. Then it was followed by the next lecture series on our training workshop on WRF modeling system, jointly organized with CDAC Pune. I think Dr. Ashish Routray was also a speaker in that workshop, I suppose, in that WRF workshop, which we conducted jointly with CDAC. Then this is then the third lecture series was conducted on satellite meteorology, jointly with BIT Mesra. And that went on for about 5 months, about 20 weeks. And this is the 4th lecture series on radar meteorology, jointly conducted by SAMA and Atmospheric Center for Advanced Radar Research at Cochin University of Science and Technology. For the information of the speaker who is new for this lecture series, in this lecture series, we have about 1,200 candidates registered from about 48 countries. As you know, besides the 9 South Asian countries, our lecture series are also open to the member countries of the non-aligned movement countries, NAM countries, because NAM SNT is the institutional member of SAMA. The syllabus of this lecture series on radar meteorology is designed based upon the requirements of the member countries, as well as based upon the advice of the advisory panel of the lecture series. Also, the speakers of the lecture series are generally distinguished scientists or senior professors. Many of them are even retired also sometimes. So we have a very distinguished panel of the resource person or speakers. At the end of the lecture series, we will conduct a online test in which we shall give the certificates to the participants based upon their scores, like outstanding or excellent or very good, depending upon their score. We also give the attendance certificates to those candidates who receive or who have more than 75% of attendance. So our lecture series has got a very good viewership on the YouTube, because all the lectures, the past lectures as well as the present lecture, is being telecast or live cast on the YouTube channel of SAMA. All the past lectures are also available on the YouTube. So especially for those participants who are from the country which are having different time zone than India, and so they can watch the lectures even afterwards. All the participants are requested to write down their questions in the question and answer box, and it will be answered by the speaker at the end of the lecture series. So thank you so much, and enjoy the lecture. Have a good day. Over to you, Dr. Srikala.
Thank you very much, sir. Now I invite AVM retired Professor Aditya sir to deliver presidential address.
Sir, please unmute.
Sir, please unmute.
Am I audible now?
Yes, sir. Yes, sir.
Thank you, Dr. Srikala, and it's a great pleasure to have 17th lecture being delivered by Dr. Ashish Routray, a man well known in the NWP field, and his work on data assimilation had been pivotal in assimilating the radar data. As you see, last 3 lectures we have been trying to explain the importance of data assimilation, especially the radar data, which is becoming so, with the number of radars increasing, its availability is going to increase in the time to come. It's already 37 radars are there, but will reach number 250 shortly and may touch 100 in coming years. So this data is valuable. We have seen that particularly in the nowcasting and short-range predictions, radar data plays very important role, and I am sure the work being done in the NCMRWF to assimilate this data, and particularly the high resolution model of 1.2 kilometer, 300 meters, urban level forecasting will be a great help. I'm also happy to inform that in the country we have got now supercomputing facility of about 22 petabytes, and of which the NCMRWF has got 8.24 petabytes of computer installed already. So it will give a boost to both the research activity and as well as the operational work being done at the NCMRWF and other institutions. So it's a great time now for radar community, for the NWP community and the operational people to make use of these facilities, radar network and the high power computing, so that we can really make a difference as far as the quality of forecasts and warnings are concerned. So once again, thank you to the organizing committee, Vilas and his team, and ACARR, CUSAT and the ECT team of the SAMA, and we have Mohan joining us today, and also the Anikanda. So welcome, and all our veterans, Millie, Swagata, they are here as to support. So the series have been a great, I think, success, having eminent speakers to participate and deliver the talks. And as mentioned, these talks are available online, and I'm sure you should make full use of it. Thank you and have a great day.
Thank you very much, sir. Now I invite Dr. Anikendra Kumar to give a brief introduction about Dr. Ashish Routray.
Yeah, thank you very much. So I am just sharing a screen. Is it visible? Is it visible?
Yeah, it's visible, but you can't.
Okay, thank you very much. So it is just a brief introduction to the Dr. Ashish Routray. So Dr. Ashish Routray is currently working as a scientist at National Center for Medium Range Weather Forecasting, NCMRWF. It is under the Ministry of Earth Sciences, and he has joined the NCMRWF, Ministry of Earth Sciences, in the year 2029 as a senior scientist. And he received his Master of Technology degree in Atmospheric Sciences from the Andhra University, Visakhapatnam, in year 2002. And after that, he also got the PhD degree in the Atmospheric Science from the Indian Institute of Technology, Delhi, in the year 2009. And his research focus is on the mesoscale modeling, radar data assimilation, land and atmospheric atmosphere data assimilation, monsoonal studies, and studies of the extreme weather events and the regional climate modeling. Dr. Routray has also received the Ministry of Earth Sciences Merit Award in year 2022 for the outstanding contribution in the field of atmospheric science and technology. He also received the Indian Meteorological Society Best Paper Published Award in year 2016 for the modeling study on the atmospheric and the oceanic sciences. Dr. Routray is one of the subject expert of the Board of Studies in the Department of the Atmospheric Sciences, Central University of Rajasthan, for the period of the 2 years in between 2022 to the 24. He has also visited many reputed research centers, such as the national, this NCARR, NCEP, Purdue University in the United States of America, as well as he also visited to the UK Met Office as the visiting scientist. He has also published more than 60 research papers in the international or the national reputed journals, and he has also about 20 book chapters along with the 12 scientific reports. So thank you very much, and over to you, Dr. Sri.
Thank you, sir. Dr. Ashish Routray, sir, please start the lecture.
Good afternoon, all. I sincerely thanks to Professor Das sir, Professor Tyagi sir, and all my friends and colleagues. Now I am going to talk about the radar data assimilation in NCUM regional UK Met Office model. So I'll share my slide. 1 minute. Is it visible?
Yes.
Yeah.
1 minute. So I'll talk about Doppler radar data assimilation in a high resolution NCMR model over Indian region. So last lecture, Dr. Anand has shown this model. So from the last 2 decades, I am working on the Doppler radar. I developed all the assimilation scheme of Doppler radar assimilation in WRF. Now we are also develop some schemes to assimilate Doppler radar in UK Met Office, mainly using the Indian Doppler radar. So So why we have a radar data assimilation? First, before we go into radar data assimilation, we should know what is the importance of radar data. Because there are wealth of Doppler radar observation from ground-based to air-based and also movable. But in India, we are mainly the ground-based radar. So slowly, Ministry of Earth Sciences is planning to flight-based and what is the importance of radar data? So, and this is airborne and movable radar. Assimilation of Doppler radar data should improve the small scale structures in the initial model, initial condition, and it reduces the model spin of time. If you have any mesoscale model, if you have assimilation, any observation data, it has a spin of time 2 hours or 3 hours. So depend upon your resolution and depend upon your time of running of the model. So is a spin of time is very important. So it reduce the spin of time and enhance the short forecast of NWP scheme. So for increasing the precipitation on time as a location. So it is a very important parameter. So every model, every forecaster wants to improve how the precipitation or rainfall will be timely and location specific. So that is a very important aspect to predict that parameter. So when you have assimilating radar observation, so the precipitation of forecast is increase with the time and the location. Huge amount of data in storm mode. If you have a radar is off the storm mode, so it will be collecting huge amount of data. If you imagine 3 million of data per 5 minutes from one radar. If you have a 37 radar over the Indian region, so how you will handle that much data in your assimilation system? There is some limitation in assimilation system, and also you have to store it that data in your local machine and quality control. So that is a very huge tax to assimilate this observation. So these observations are high spatial, which vary from 2 meter, 250 meter to 1 kilometer, and also temporal resolution 1 minute to 10 minutes. But coverage is limited to a region with a reflector. As you know, the radar will not cover the one radar cannot cover the whole India. If you have a certain limitation, if you have a 250 kilometer or 300 kilometer radius. So with increasing our computing power, also our knowledge in advanced data assimilation technique and experience in cloud scale modeling. So now we are moving towards how we will assimilate all this huge amount of data with a high spatial and temporal data in your high resolution mesoscale model to improve your forecast skill. So already you had many speakers have spoken about this assumption in radar technology. Just I'll touch about if you have going any radar technology or radar data, we should know what is the limitation and what is the benefit and how we will be tackle all these assumptions. So in our mind, we will see the radar technology not only total perfect, we have the certain assumption. You see calculation of radar reflectivity and other variables are based on 5 main assumptions. And about the radar beam, the target and the atmosphere. The beam travels at the original inclination angle. We assume the whatever radar is sending the electromagnetic, it will travel in the original inclination, whatever the angle. But it is not true when it is passed through the atmosphere. The target observation observe very little of radar electromagnetic energy. So we assume the whatever electromagnetic energy is transmitted by the radar, it will come back to the radar. But it is not true because it is observed somewhere in the atmosphere. Many things are available over the atmosphere. So it is observed or diverted from some one place. So we have to assume that. Target particle are small, homogeneous precipitation sphere with diameter much smaller than the radar's origin. It's a very important. We have to follow this Rayleigh scattering of the radar. Particles should be small, and one important aspect is whatever precipitation over an area of tube, it should be homogeneous, but it is not a real wall. It is not true. So all targets are either liquid or frozen, not the mixed phase. If you have a mixed phase, then there is some error in the radar. So we have to understand the radar has only the liquid and frozen state of the hydrometer can be targeted. Targets are uniformly distributed throughout the sample volume. If I take a volume of the atmosphere or cloud, it should be whatever some hydrometer is there, it is uniformly distributed within that volume. So in that assumption, so how we detect precipitation? The degree of detection of precipitation target is depend on a variety of factors. So I already discussed this radar assumption. Then if you come to the real world, there is some issue in when we have a target in precipitation or cloud. Atmospheric condition between the radar and target. It is very, very frequently and different weather scenario or phenomena within that radar and target. So target characteristics, it depends upon size distribution, phase of water, it may be liquid, it may be ice, or it may be mixed phase. So we have to understand that characteristics of the target. Then distance from the radar to target. What is the distance between radar and the target? Radar characteristic, power return, how much power, frequency or wavelength, antenna gain, beam width, pulse width, we should know. So if you see, I have written in 2 colors. One is red and one is blue. So red point are unknown. Some need some approximation. But the blue points are known factors because we know our radar and we know our radar characteristics and all these things. So how we tackle these red points? Atmospheric condition between the radar and target characteristics. But already previous slide I told this radar technology is a 5 assumptions. So in that assumptions, and we have get a wealth amount of observations, and we consider whatever assumption and whatever condition within the radar technology or atmosphere. So we consider the radar data is a good data, and it should be utilized in our NWF model. So how will we utilize this this radar data in NWP? Because it involved with the various assumptions. So it need a quality control. We cannot directly assimilate this radar data in our model, just making a suitable format. No, it's never. It should be a quality control. Quality related issue have become the main research field for the radar data user rather than assimilation. If you have a good quality control packages and good quality algorithm, then we can assimilate. But the radar data assimilation, if you have a convert this radar data into suitable format, it will be accept the model. But what is the utilize? What is the impact? What is the role of this radar data in your analysis? Whether analysis will improve or ruin the analysis. So best is fast to emphasis and fast most is to quality control. So already my colleague Dr. Amar Jyoti has talked about this quality and all this. Then radar derived the precipitation data are burdened with a number of errors from different sources. I already talked meteorological sources and non-meteorological, that is technical sources. So I have to consider these errors, how to remove or how to assign these errors in my model. Precise information about the data reliability is important for the end user. So precise good information should, after quality control, we should get a good information from that. Once we get the good information, good data of the radar observations, then we can go for the assimilation. Radar-based precipitation forecast, severe weather warning system have become a fundamental part. Now, based on the radar data, we can precipitation forecast, we can give the severe weather, how the severe weather move from one place to another, how severity is there, and which area is affecting after 1 hour or a half an hour. So where we get this error, sources of error. So different sources of error, hardware sources of error, antenna accuracy, signal processing, and wavelength. So non-meteorological error, electromagnetic, biological echoes, beam broadening, range. I'll not go one by one and all this. Already you had this, all this. So just to brief about this is the errors and this is the problem in the radar data. So before going to assimilate, we have to tackle all these errors. Meteorological errors, beam attenuation, water vapor, if you have dense cloud, rain, snow on the radar, if you have some rain or snow cover your dome of the radar, it has also attenuated the beam. Anomalous propagation, attenuation due to hydrometers, appropriate use of exact radar relation coefficient. We cannot apply one radar relation to all the radars. It has different from one radar to another. Then bright band effect. If you have after 5 kilometers, it's a ice phase. Once this enter to the atmosphere, then it have a mixed phase. How we will be tackle this type of error? So after doing all the quality control and other things, I got a good quality of radar data. Then what we do? So why we are going to radar data assimilation? If you compare with the conventional data assimilation and radar data assimilation, what is the importance of radar data? Observation resolution is very low in conventional data. CNOP, upper air, on this, it cannot be taken at a very high resolution level, horizontal resolution. Every variable we can get from the conventional data, but W cannot be get vertical velocity. We cannot get from the conventional data, but vertical velocity is a clear major role for the convection. Then we have this optimal interpolation balance relation from the convention. If you go to radar data assimilation, you can get a high spatial and temporal resolution of data. then we can assimilate only radial velocity and reflectivity as observed. Retrieval of unobserved fields, we can also assimilate temporal terms of essential. You can also get, if you see this picture is not a Cartesian coordinate. My model is a Cartesian coordinate, but it rather will give a polarimetric data. So I have to have convert to this data to in my model resolution, model grided or Cartesian coordinate. So radar quality control I already talked about. I will not go to that. Dealiasing, removal, sea clutter, ground clutter, so many things we have to remove. Then data pre-processing, that is very important. Mapping to model grid, because these are the polar grid. So we have to have map to model grid. Thinning, because huge amount of data is coming from radar. In one grid box, if you see one grid box 4 kilometers, 1,000, maybe 1,000, more than 1,000 can get all within 4 by 4. So how will they thin it out? It is a very important. So assigning error, each observation we have to assign error. Suitable formatting for a DA system. Observation operator we have to develop. Observation operator for radial velocity and reflectivity. So once I got all these ideas, all confident in my quality control, and radar data is coming to frequently to my server, and I am doing the quality control automatically. It is not physically or intervention of humanity. So it is all, everything is coming to the proper way, daily basis, and we have to have monitor this, which radar is down with, what is the issue, and all this. After monitoring all these observations, then we have the going for assimilation. Then when we are going to assimilation, so we have a, here I am going to show the UK Met Office model, unified UK Met Office model. It's a seamless model. It can run from global to 330 meters. So I'll focus only the over in Indian region 4 kilometer operational model. So from where we are able to give the some result, and this is the model domain, because this is the operational domain 4 kilometer over Indian and Southeast Asia, because we are providing the forecast to the BIMSTEC countries, all these Southeast East Asia countries. So we extend that domain up to 105. So these are the configuration. I will not go to the configuration because this is the model is 4 kilometer and 12 by 12 points. Take huge number of grids, and we run up to 72 hours. Also, we implement soil moisture assimilation. We are getting soil moisture from SCAT, SMAP. So we are assimilating also soil moisture boundary condition in this model. It's an operational model setup. So here I'll give some few examples before going to operational data. In our operational model, we have to have vigorously test this data for various weather events, because we cannot test all this, we cannot take into the account as a operational. So before going operational, we have to consider many rainfall events and many scenarios, dry spell, wet spell, and all these things. Here I will give the rainfall events and western disturbance by assimilating dedoppler radar. So here I am going first assimilate. We have a 4-dimensional variational data assimilation system in this model, and we are assimilating before assimilating the Doppler radar radial velocity. We have assimilated all conventional satellite observation, whatever data available over Indian region. Then we did one experiment with the radial velocity additional of whatever observation using control. So we have considered 3-4 cases, and these are the cases over the 2016. It's a very active monsoon period over the Indian region. We are considered 12 radars. During that time, 12 radars is available to NCMRWF. So we are considering these 12 radar in the assimilation scheme. So if you see this panel, right top panel, so if you see the color, it means that much amount of observation received from respective radar. If you see the Jammu Kashmir, it's very minimal observation that day we receive. So once we receive these observations, then we apply our quality control and all the quality control procedure and the formatting. And another one is super ops. already Dr. Amarjyoti told, super-ops is we cannot assimilate all the observations in the our assimilation system in each grid box. So what we do, whatever observation, good observation within that grid box, we have mean these observations and compare with our background. And if it is good, then we can consider that observation within that grid box. So in this way, we make a super observation over this. This is a Chennai radar, as a for example. So after this super ops, then go to formatting, proper suitable format and assimilate. Once we have the assimilate, then our curiosity should be whether this assimilation of radial velocity is any impact in initial condition. We know if have any impact in any modification or any improvement in initial condition, obviously there is an impact on our forecast. So we analyze all these are the stations wherever the RSW observation is available. We compare with the RSW wind and VU wind and V wind. So we found that after assimilation of radar data, the RMSE error of U or V wind is reducing. One beauty of this picture is if you compare all these observations, whatever 12 radar data assimilate, if you compare the error with other without means where the radar is not assimilating stations, if you see wherever the observation assimilated radar observation, that error is relatively lower as compared to others. So in a different threshold, ETS and others are compare object-based comparison also carried out. So here we have seen ETS is increased when we have a radar observation. You see, one things we can count, if you go the forecast hour is increasing, none of all the experiments are reducing their skills. But the skill, if you compare to among these two, so radar is well than the control. So in this different threshold, lower threshold and the higher threshold, so case 1 and case 2, we can get the similar type of result. So radar has a positive impact after assimilation in the rainfall. And if you see, go to after 12-hour forecast or 15-hour forecast, this drastically reduce the quality of this. It shows that after 18 or 20 hours, the forecast is not, the impact of radar is gradually reduced and it is merged to the control. So this is the message we have got. If you have see the lower threshold and higher threshold, lower threshold rainfall is well captured. So if you go to higher and higher threshold, the model has an inherent error. So another important aspect is western disturbance, which affect all over the northern part of the country. And then here is one issue is if you have a western disturbance, we cannot get the data over the mountains region. There is no this upper air observation, no surface observation to cover the whole western Himalaya and northwest of India, this Himalaya belt. So then we thought, why not we'll assimilate radar because it has given. But then when we go to the assimilate radar, then technically we can get this radar data. But once we analyze, then we found that a lot of problem in the radar data because it's a blockage, beam blockage, and all these high mountains and the valley. So we did some quality control. We cannot say this is a total well proof. That time only Jammu Kashmir and this Patiala and these 3-4 radars we are more focused in the Jammu Kashmir. So we did some quality control and remove all the clutters and all these things, and found that very less amount of observation is assimilated in the model when we are analyzing the western disturbance. Even though you have a very less amount as compared to continental in my previous cases, so even though the small amount of observation is assimilated along with other observation conventional, there is some impact in the western disturbance rainfall. If you see, compare this left side observation and the last one is the other one, so there is an improvement. If you have see this lower part of this towards Punjab, Haryana region, the rainfall is increased, which is not found in control. So all these cases, we see there is some improvement in radar assimilation, but it needs very high quality control, because now we have a 9 X-band radar over this Himalaya region, Uttarakhand, Himachal. So our main objective is how to assimilate this 9 X-band radar, because it is giving very huge information and data. So how now we are focusing how to assimilate this X-band. We are already capable to assimilate C-band and S-band, because there is no much quality control is required. That is required, but that is not much critical as compared to X-band, which were installed over the Himalaya region. So that type of work we are now taking care of. Near future, we will assimilate 9 all X-band radar over the Himalaya regions. So these are the improvement we are getting, but not much improvement. If you see the compare the RMSC, and it is 0.07, it is 0.04, correlation is more over the same, and all the cases. But however, there is a message to the community: if you assimilate more and more observation over the Himalaya region, because we have data sparse region over the Himalaya region, so we can get a beneficial in our forecast, in cloudburst observation and all these things we can get. So, but for this study, we need very high level quality control package. So overall, we can get a positive response from the, if you see the ETS, and below one object-based things, because ETS will give the special distribution of the rainfall. Rainfall amount is this 5 millimeter, 10 millimeter, 15 millimeter, this like. But this object-based method will give you all the scenario. What is the structure of your pattern? Structure, amplitude, and location. That will give you more, more means confident what is going on in my model, whether structure of the rainfall is well captured, or amplitude is well captured, or location is differ from one location, observation showing somewhere, and my model is showing shifted somewhere. So this type of object method, based method, we have to apply. So in this object-based method, S stand for structure. You can see the structure, what is the structure of the rainfall, and all these things. Structure is well captured. Both the model, control and radar, and if you compare among these things, the radar has little amount of improvement in the structure. If you see, go to the amplitude, this both the model is showing high amplitude rainfall over this Himalaya region. So, and after assimilating radar, so then this amplitude is quite reduced, and location also shifted. If you structure compared to location, the location is more error, and if you see the amplitude, and amplitude has high error rather than the structure and the location. So how we will be emphasize how to reduce this type of false alarm over this region. So this is a very good objective analysis, and we can give an impression how we will be reduce this amplitude intensity, which is false alarm is going to more, means as you compare this intensity scenario. So then this is the before whatever we have shown this is the radial velocity. Then we thought about, okay, radial velocity, whatever way we can assimilate it and quality control and give a positive, why we will not go to further reflectivity? But reflectivity is very critical and very crucial. Without proper quality control and all these things, we cannot assimilate directly to the model. So it will create a lot of problem in the model. So then we thought, why will go to directly assimilate the reflectivity? Why not to convert into a rain rate from the reflectivity? So once we are able to convert the rain rate, this is a very new work over the Indian region. None of the no one, if you see this type of study cannot find before this our study. So if you see this all this technology and all this, you can find by paper Journal of Hydrology. So when we successfully convert the reflectivity to rain rate with minimal quality control and all this, so we apply latent heat nozzle. It's a very old technique, technology, and many of the other operational center, UK Met Office and other countries, they are also applying latent heat lodging for a rainlet rather than assimilation of direct reflecting. So based on the observation, relatively little moisture is stored in that. We know that if you have a cloud, then the observation, if you see the moisture is very less, all are precipitated to the as a rain. So we consider whenever the cloud and precipitation, the column of integrated latent heat rate must be approximately proportional to the net precipitation rate. Whatever precipitation will occur, so we thought this is a column integrated latent heat rate, because we know the cloud will not store much moisture within the cloud, so it will be precipitated. So we applied that latent heat nudging procedure, profile latent heating scale by ratio of model as well as whatever rainlet observed precipitation from the Doppler radar. So I'll not go detail. So we mostly it will be impacted the temperature, often the moisture. So if you want to go to detail, you can John's, Maxfors, and then my paper, this is Routray, we are very precisely define all this methodology, how it is assimilating and all these things. So here is just a brief schematic. So when we will apply. So if you have a radar measurement, then we only can on the latent heat nudging. Once we have a latent heat nudging on, then it will search precipitation observed by radar, whether it is observed by radar any 0.mm per hour. If yes, then the scheme will be on, then precipitation generated by the model. It will be compared with the model, because I told ratio of the model precipitation rate as well as the observed precipitation rate. So once the ratio, then we have the scale of latent heat ratio profile, and if not nothing, if you have a so no, then it will be do nothing. So this is the schematic, and this each box clearly described in my paper. So once we have a assimilated that latent heat nudging, and we see the RMSE in the, I already told, if you see the temperature theta, it have a much impact rather than other. So Q have also impact. So once we have seen this analysis time, then our confidence level is increased. Yes, my latent heat nudging or whatever I am applied, it is properly assimilated. Then we can go to the forecast and all these things. So if you see the upper panel is our IMD NCMRWF merged rainfall, and this is top right side is our Doppler radar from Chennai, and this is control and the nudging experiment. So it is clearly showing over the oceanic region, this patches is well captured by the latent heat nudging, and also the coastal part of the Chennai and others. But if you see one thing, weight bias is over the northern part of Chennai. So if you are getting some positive result over the oceanic region, then another error is coming from this. So what is the way how to remove this weight bias? So how these things will be adjusted with the model and the observation. If you see, if you think about latent heat nudging is just comparing the profile of your latent heat of the atmosphere. So if there is no model as a no rainfall during that period, but observation has some latent heat, so how will we compare? So this is the issue in the model, because model is not able to capture the exact amount of rainfall during the initial phase as compared to observation. These are the create little bit issue in the dry bias. And but it's wherever the rainfall is there, then there is no issue. That means model is giving certain false alarm after assimilating that. So then we can think about what we'll do next. So another case also, you see the good amount of observed rainfall is captured if you compare to control and latent heat. So it is have a positive, and certain places have a weight bias. So then we move to, again we have applied contingency rain area object. This is another type of object base. You see I told the high amount of rainfall occurring when the latent heat nudging is applied. It is clearly showing object based. If you see the volume, error is higher than the displacement and pattern as compared to the control and other part of the LHN. If you see the volume, I already saw this volume of amount of rain is occur over this region. So clearly object-based method is showing the volume is high after the assimilate of rain rate. But if you see displacement and the pattern is well captured as compared to control. So we cannot say if you have assimilate radial velocity and rain rate, it will give the exact amount and exact volume of no. That is some issue in the quality, maybe quality control, or maybe the model, how the model is spin up, how the model is releasing the this rainfall. So we see the amount is so impact of Doppler DWR reflectivity on simulation of rain. Any question? Excuse me? So then we thought, why not we'll assimilate? Then slowly we have a ideas, and we can get some good quality of reflectivity, and we assimilate that reflectivity directly rather than the rain rate. So before going to reflectivity assimilation, we have a processed data, and this left side is your raw data, and after quality control, if you see this scale, zero data, zero, if QC is zero, data quality is not set. If QC1, reflectivity below the noise level, and if QC3, clear sky, so we have this indexing, this radar. If you Q0, then if QC, then we have a data quality, and there is no quality, and whatever data is assimilated. So this way we have a quality control and a good experiment. So this time we have a more observation available. Around that time 12, now it is another 6. We added 18 radar data, and if you see assimilated observation, these are the number of observations assimilated from conventional way. And if you see this left below panel, we have these observations from different radar stations, radial velocity, amount of radial velocity, and reflectivity assimilated in the assimilation cycle. So we have considered a few rainfall cases during the peak monsoon period. If you see the compared to control, clearly showing it has improvement over the coastal of Odisha, and it has a pattern, and the intensity also improved. If you see the along the coast, there is no rainfall in the control draw. Similar, another 7th September of 2023, the rainfall over the Mumbai region also improved. So this way, it may be a one cases. No. So we have considered few active phases of monsoon of 2021 also. So we found that in a monsoon region, the peak monsoon region over the central part of India is improving as compared to control. So this way we have assimilated the radial velocity and the reflectivity in the 4 kilometer regional model. So now once we have developed our algorithm, our capability, then we thought, why not we go in a rapid refresh, high resolution rapid refresh, frequent assimilation, 1 hour. This is a 6-hour assimilation. So we developed 1 hourly update HRDA system with a high resolution, 1.5 kilometer resolution based on NCUM model, and another is based on WRF model. So briefly, I touched this result. So this is based on UM model, because we have no competitor. It is taking a lot of time. If you run the whole Indian domain point 1.5, so divide the 3 domain, domain 1, domain 2, and all this. So this is each domain have a 1000 by 1000 domain. So we run every hourly rapid refresh, every hour 72-hour forecast. So we analyze and very heavy rainfall cases over the Mumbai region, and found that there is a positive signal in the HRR system if you compare operational, control, and all these things. So then we consider 2 thunderstorm cases over Northeast India because we have 3 domains, and this is already accepted in the book chapter of edited by Dr. Someshwar Das. So these are the positive result we are getting from the HRR system. Now it is going to operational in the new computer, not in the 3 domain. It will be covered the whole India with 1 kilometer or either 1.5. We are planning for 1 kilometer. If the computer support, infrastructure support, then we run the 1 kilometer run over the Indian domain where we are running currently in 4 kilometers. So then objective based analysis, and we can get the good result and vector displacement error or these things. So then prediction recent cloudburst through WRF GSI based 3D map HRR system. If you see, there is a very high cloudburst is happening during the years. So we thought, why not focus on the Himalaya, our Indian Northwest Himalaya region. So we have 2 domains. One is 5 kilometers. This is also a 1 hourly assimilation, but in the resolution is 5 kilometers. But we more focus on the domain over the Himalaya region. This is the Zoom domain where we have a HRR. Both the domain have a HRR, 1 hourly assimilation. So then we are consider these are the observation and the amount of observation going to each domain, and these are 2023 cases. Of many cases we are considered 11 cloudburst cases we have considered over this region, and this paper is now going to submit in atmosphere research, and we found this is the synoptic condition during the period. So lot of moisture is pumping towards the Himalaya region and all these things. This is August 2023. So if you see this 13 August 2023, how the cloud structure over this region in 5 kilometer and 1 kilometer. You see, if you go to higher resolution, the finer scale of the mesoconvective system is well captured as compared to 5. But this 5 kilometer also showing a good result. But if you compare both model domain, is have a 1 kilometer have a good result. So special pattern of the rainfall GPM and this 5 kilometer and 1 kilometer, you see the patches is captured by both the model, but the intensity is improved in the 1 kilometer. If you see the below line time series, you see first peak of the model rainfall is somehow captured both the model. You see the second intense rainfall, none of the model is captured. So what is the issue? So here, how many radar data is going? Because this is all the X-band radars. So now we are exploring why the second peak is not capturing. Because you see the first peak is capturing. After a certain time, it is not capturing, it is flattened. So this is the issue. Even though we are going to 1 kilometer, or even though have a 1 hour assimilation, there is some issue. So we have to dig out what is the issue. It may be how much assimilation data is assimilated and what is the quality of. So we are exploring that angle, and we are also exploring how will we assimilate good quality of data in that HRR system over the Himalaya, because it's a very tricky and it's a very dangerous region. So we are planning to assimilate this X-band radar over this region. But say give this result, we have a confidence, and we are test operationally over this region, and very soon in the new computer facility we will give the 1 kilometer to IMD and other region and extend to Northeast region. Thank you. Have any question I can like to answer.
Thank you very much, sir, for your interesting talk on DWRS data assimilation. So before starting this question answer session, now we can have one photo session. So I request all of you to switch on the camera.
Anikendra may not be here. Dr. Mohan?
Aditya, sir.
Tyagi sir was there. Dr. Mohan, Dr. Tyagi, sir.
So I think we need to manage by this.
Yeah. Okay. I think we'll
Okay.
take a short. Yeah.
Okay. It's okay.
Thank you.
Okay.
Now I request Dr. Swagata sir to moderate the question answer session.
Thank you, ma'am, and thank you, Dr. Ashish, for a nice presentation and finish in a proper time to do a longer questionnaire. Okay. So the first question which we have is, please explain in detail about the spatial resolution of different types of DWR.
So this is already explained by Dr. Pradhan in our past 2-3 lectures. The DWR have a different resolution. If you go to C band, it will cover very low areas, means not the high as compared to S band. And if you go to X band, then it is another radius of it's maybe within the 100 kilometers. C band may be sorry, X band may be 50 kilometer radius. C band may be 100, or if S band it can go to 300. So that resolution depend upon the weather pattern, what is approaching the radar station. If you have a no weather, then they have a not of the on the model the radar up to the 250 or 3 kilometers. It is very low have volume scan, and this is it depend upon the weather pattern. And generally, people are taking 250 meter to 500 meter resolution, spatial resolution of radar.
Then all C-band radars have same spatial resolution?
No, we say if you see that is depend upon the radar station. It's not equal, but now IMD is specify all the resolution, all the volume, the scan is the same.
Is
Now,
the model open source?
This NCUM is not open source. This is a licensed version.
And then what are the advantages in comparison with WRF?
We cannot say that what is the advantage and disadvantage in the sense, because different people have a different aspect of to run the model. So we cannot pinpoint this is a good model or this is a bad model as compared to WRF. So this is a very tricky question. We cannot comment on that.
Yeah. How effective is this model in predicting cyclone tracking?
So in as an overall sense, if you have a cyclone in a Bay of Bengal and Arabian Nios region, the NCUM is showing good as compared to our GFS. And certain time it have a not all the cases, but many times NCMR is going to genesis and intensity is properly captured by NCM. So it's not 100 to 100%, but as compared, every time we are comparing with the IMD GFS and our NCM each cyclone, and every year we have a report. So we found certain cyclone is not capturing by NCM, but GFS is. But overall, it is good to genesis and intensity.
Okay, one question from YouTube now I am reading from Gaurav Tiwari. If there are n numbers of radar available, which provide m number of parameters, here parameters mean data, then how to decide the kind of observation that gets selected for the assimilation?
So first I am clearing the observation parameter, n parameter. This is not n parameter. This is the only 2 parameter we are able to assimilate: radial velocity and reflectivity. So once you have a many of radars, there is a overlap. So we have to have develop our scheme, quality control and all these schemes. So overlapping parts should be removed, and we have the emphasis which radar is this target of atmosphere is close to the which radar. That is beam burning and all this scenario will come to picture. So when overlapping is there, then we have to develop not the simple quality control which now we are using. So we have to develop how the overlapping part will be managed. So that overlapping part will be reduced, and which is target is close to that radar, then we will consider that, not the second or third radar. So that type of things will be definitely developed in near future once we got this type of overlap and data. So US and all these WSSR, AP, they are overlapping over Oklahoma and all this. They are developing very good quality package. And I clearly say that nobody can share any quality control package to anyone. So user have to develop their own quality control over the region. So if I can ask someone give me your quality control, it may not be applied for our radar because our company and all these things is different. Our weather pattern is also different. So we have to have developed our own quality. It's a big science to develop quality. Once quality control, then we can assimilate. No, there is no mistake.
Okay, thank you. One more question I didn't get very well. How do you define structure of an event in objective analysis?
So structure, if you have a see the extent of how the structure is means what I can say structure, what is the extent of the convective system. So if you have a strong convective system, then your intensity and structure is different. Okay. So the objective analysis is compare with the observation and then your model forecast. So then decide.
Okay. Then one very basic when in the preparation of the data. How radar data from all 37 radars are converted as initial condition in DA?
So I already told we have a well-proved quality control package and a system. All when we are getting radar data, immediately they will analyze, and each radar has a different code because Delhi radar, Chennai radar have a different code. So this code, whatever available within that particular folder in the FTP server. So once this code is available, the program will fetch out and quality control and prepare the data and different elevations. We are not tracking the one. It's a different elevation, 11 elevation. Each elevation have data. Then we have another package to combine all this data. It's depend. If I am using NCUM model, my package is grid format. So I will pack this data in a grid format. If somebody using WRF, this is maybe next or littler format. So we are giving this data at a point. So all are in NetCGF. Then after that, individual modeler or individual operational use, they can use it there as per their requirement. This is the intermediate program. But in NCMRWF, IMD, from IMD server to NCMR, it will be come to one folder. Each radar have a different code. So from this code, the program will fetch out, quality control will run, everything, and then store in as a NetCGF finally on different elements.
Yeah, the next question maybe you can answer by just one line. Will different elevations in different radars affect DA?
We are getting same elevation because IMD is fetch out. All radar will be provide the same elevation.
Okay, someone has requested, I have a search on hydrological modeling. Can anyone help? I think
hydrological modeling, we are not concerned about hydrological modeling. Maybe he is searching for this my paper, Journal of Hydrology paper. Maybe.
Okay. So now how data control in data assimilation in DWR data retrieving during observation, that you already answered in different way. Do you want to answer again?
No, same way we have a quality control package. It's a no human intervention. Once we have tested, full tested, we hand over to our operational people. So it will run automatically. If any error, then we can intervene.
And again, I'm asking this just by this. So whenever you ask the question, please mention the name of your country, because sometimes the questions are very basics. So if we want to answer very specific way, it will help us. Like the last question from him, the use of the radar data in a research application.
So it's a very important.
Related to that, but
Uh-huh.
still mentioned by 1 or 2 sentences.
Because if you have a study the very location specific weather pattern, because now we are going for location specific, her motion means that type of NARA, then we have to go to high resolution and very location specific and a mesoconvective system, and that's why we have to have assimilated that data in our NW model. So research is very important on the radar nowadays.
Yeah, thank you, Dr. Ashish. I think all the questions were answered. If any of the panelists need to ask, then they can ask. From my side, it is over, Dr. P.P. Sikor.
Thank you, sir. Now I request Dr. Millie Ghosh to extend vote of thanks.
Thank you, ma'am. Now I'm sharing the screen. On behalf of the organizing committee, I extend my heartfelt gratitude to each one of you for your contribution for this 17th lecture of weekly online lecture series on radar meteorology. Firstly, I would like to thank Dr. Someshwar Das sir, Secretary SAMA, for giving welcome address and brief information about this lecture series. My deepest appreciation goes to ABM Professor Ajit Tyagi sir, President of SAMA, for insightful presidential address. Your gracious presence without any miss and your guidance for each and every minute details is the key for successful conduction of every lecture of this online lecture series. Now I would like to thank our speaker of the day, Dr. Ashish Routray sir, Scientist App, NCMRWF, for delivering wonderful and very informative lecture on DWR data assimilation in NWP models. I also thank Dr. Anikender Kumar sir, IMD New Delhi, for introducing our today's speaker, Dr. Ashish Routray sir. My heartfelt thanks goes to Dr. Swagata Paira, Associate Professor B.A.D. Misra, and Treasurer of SAMA for nice conduction of question and answer session. My sincere thanks goes to Dr. P.P. Srikala ma'am, Assistant Professor CUSAT, for moderating this session very wonderfully. Finally, we express our heartfelt thanks to all the participants and attendees who joined us from across the globe. Your presence and active participation plays a key role for the success of this lecture series. Last but not the least, I want to thank Dr. Abhilash sir, Director ACARR, CUSAT, and Program Convener with all his team members, Dr. Rakesh B. and all scholars, for their constant support in organization of this lecture series. Thank you, sir. Thank you all.
Thank you all.
Thank you, ma'am. Now I request Someshwar Das sir and Ajit sir to give some concluding remarks.
Okay. Thank you very much, Dr. Srikala. Thank you, Dr. Ashish Routray, for the very interesting talk that you have given. You have covered almost everything about the radar data assimilation which is being done at NCMRWF. You have reviewed starting from the data processing and the quality control, just a minute. And also shown the impacts of radar data on the simulation of different types of events. This is a third lecture in sequence devoted completely to the application of radar in NWP. As you know, the first talk was given by Dr. Amar Jyoti, also a scientist at NCWF. and she presented about the details of radar processing and quality control, which is a very important task before you can assimilate any data. Then it was followed by a detailed lecture about the assimilation of radar data in the WRF model by Dr. Anand Kumar Das from IMD. And this is the third lecture about the radar data assimilation given by Dr. Ashish Routray. As you know, he has been working on the NCUM regional model. And so his talk was basically oriented toward the assimilation of radar data in the NCUM model. And as rightly said by him, that especially when you have to forecast the convective scale system like the thunderstorms or hailstorms, etc. In that case, the assimilation of Doppler weather radar data becomes very, very important, and it has got a good impact. I could see that there were many questions asked on his talk, and I know that, of course, many of the attendees are quite novice about this field. So probably they do not know about the complications of the data assimilation, first of all, and in particular about the assimilation of the radar data, which is so crucial. Many people have been asking now, what is the resolution and what is the coverage, etc., etc. Well, as you know, I mean, the basic parameters which is observed by the Doppler weather radar are the reflectivity and the radial velocity. And using those two parameters, you can interpret many atmospheric parameters, using different algorithms. So some people can convert the reflectivity into rainfall, because rainfall also is retrieved from the radar based upon the reflectivity itself. Dr. Ashish had also discussed about the assimilation of the latent heating by Doppler weather radar observation. Well, Doppler weather radar does not directly observe the latent heating, but indirectly, yes, because it can provide scale fall, and which can be converted into latent heating, and so that can be assimilated into the model. If you are familiar with the assimilation procedure, then you may be knowing that the model can assimilate generally those data which are the prognostic variables in the model. And so if they are not, then the observations are converted using an observation operator that was discussed last time by Dr. Anand Kumar Das. So the role of the observation operator is to convert the observation which are unfamiliar to the model into the model's language, that means the parameter. So also the rainfall retrieved by the radar, or the reflectivity observed by the radar, or even the radial velocity. So it's quite a complex thing, and those who are interested in learning more deeply about these things, you should go through these lectures, especially the last lectures about the assimilation of Doppler weather radar data. And also all the past lectures are available, so you can go through all the lectures as many times as you want to get a more clear picture of what the radar meteorology is, and how it is utilized not only for diagnostic purposes but also for NWP purpose. So you can go through lectures to understand more about that. Well, I think next Saturday will be a holiday. There is no lecture on 12th of October because there is a Dasara holiday, gazetted holiday on coming Saturday on 12th. But after that, again, we will have lecture on 19th of October. We will resume it on 19th October by Dr. T. Naranda from, I think, Tirupati, Gadangi. That will be his second lecture. So all of you get ready. And I think we are now almost come to the end of the lecture series, because today was the 17th lecture and 3 or 4 more lectures are left. Next by T.N. Rao, and then after that, I think by Dr. Avilas, and then one more by Dr. Mohan. And we are trying our best to get some expert from one of the industry like, whether Baisala or Bill or whatever, to also deliver one lecture. And after that, next lecture series will be over, and then as usual, a test date will be announced for the online test, and then also there will be a validity function. So thank you very much once again, Dr. Routray, for the nice lecture you have given.
Thank
And
you,
on
sir.
to you, Dr. Srikala. Yes.
Thank you, sir. Aditya, sir, can you give some concluding remarks?
I guess that is available.
If
Yeah,
he's not here, I think we can wind up the
No,
session.
he is available. Yeah, I think he was
Yeah.
just unmute. Please unmute, sir. I think your mic is mute.
Okay, sir.
Is it audible now?
Yeah. Now it's
Okay.
audible.
Thank you, Dr. Srikala. And I joined Somesh in conveying my appreciation for the very, very insightful lecture given by Dr. Ashish Routray. You see, the difference between academic lecture and the lecture which is given by someone who is working with the real data in operational mode. So this lecture shows that fine aspects of data assimilation of the radar, especially the mesoscale systems, which are so important for the nowcasting and severe weather forecasting. And as I mentioned you, we are in the process of acquiring more radars, high quality radars, dual pole, and also the computing power is increasing in the country. So it's up to now the meteorological community, the researchers and academicians to work on this field and contribute for the improvement in the weather forecasting. So once again, thank you, ACARR team led by Abhilash and Srikala for organizing this series of lectures. Each one is unique, but as we come to the closer next 3-4 lectures, we should reach out to more number of our participants. And as mentioned by Someshji, we are trying to get from industry some speakers to tell you about the new developments in the radars and what all is happening. So thank you so much and have a great day.
Thank you, sir.
Thank you very much, sir. Thank you, sir. So I think we can wind up the session now.
Yep.
Thank you all.